All set.
Okay, so we can start, Catherine?
Yes.
Okay. All right, so thank you for joining us today. This is part of the Hariri Distinguished Speaker Series. This is a speaker series that is organized by the Hariri Junior Faculty Fellows. And the series this year is focusing on the interface between machine learning and causal inference. Would like to recognize the Hariri Junior Faculty Fellows who are organizing the series: Anna Fishbein, who is in biology; Jonathan Huggins, who is the host today, he's in math and statistics; Jonathan J. in community health sciences; Sharik Mohammed in the School of Public Health in biostatistics; Prasad Pratil in biostatistics also, and Jinglong Zhao, who is in the Questrom School of Management in Operations and Technology Management. So I will just very briefly introduce Jonathan, and Jonathan will introduce our speaker for today. So Jonathan Huggins is an assistant professor in mathematics and statistics at BU, and he is also affiliated with the Faculty of Computing and Data Sciences, the Department of Computer Science, and also the BU program in bioinformatics. Jonathan, floor is yours.
Thanks, Giannis. Yeah, I'm delighted to introduce today's speaker, Dr. Jennifer Hill. She develops and evaluates methods that help answer causal questions that are vital to policymaking and scientific research. Her most recent work focuses on Bayesian non-parametric methods that allow for flexible estimation of causal models and are less time-consuming and more precise than traditional computing methods. These approaches intersect with other causal inference topics such as common support violations, sensitivity analysis, and estimation of heterogeneous effects. She has co-authored 2 wonderful books on applied Bayesian analysis, published in many leading statistics and applied journals, and is widely cited. She is currently the director of the Center for Practice and Research at the intersection of Information, Society, and Methodology, PRISM, and co-director of the Masters of Science program in Applied Statistics for Social Science and Research at NYU. Thanks very much, Jennifer.
Jennifer, if you allow me just a small logistical note.
Yes.
That for those of you that are participating, feel free to put any questions in the Q&A, and we'll hold the questions until the end, and then Jennifer can answer the questions that you have posted. Also, the talk will be recorded and will be available on the Hariri Institute YouTube channel after the talk. Thank you.
Great. Thank you so much for giving me this opportunity to talk to you today. I'm going to talk about machine learning and causal inference, and particularly with a focus on heterogeneous treatment effects, and try to convince you that this algorithm that I didn't create, but I advocate for a lot, BART, Bayesian additive regression trees, is a great way to go. But more generally, you can think of this talk as promoting machine learning for causal inference, particularly in a Bayesian inferential context. And I'll try to sell you on why both of those things can be important. Okay, so this talk reflects joint work with a bunch of collaborators, and particularly the most recent work has been strongly influenced by Vincent Dorey and George Parrott, with whom I could not have done this work. Anything you see you don't like, blame on me. Anything you see you do like, attribute to them, please. I also want to acknowledge funding from the Institute of Education Sciences, who have been very generous in their support of me, as well as the Office of Naval Research. Okay, and if you hear barking in the background, I apologize. My dog is not very happy about being locked away. Okay, so why should I care about causal inference? Hopefully, if you're here, it's because you do care about causal inference, but just taking a look at newspaper headlines on any given day, you will see that people care a lot about causal questions. And often if a headline or a research question is not posed causally, it's because it's been misposed. almost always what we care about in policy and in science more generally is an answer to, if I change this, would it change this? So I will give 2 quick motivating examples to help us understand why, if we get these questions wrong, we risk losing money, time, potential, and possibly even lives. So I'll first talk about the Salk vaccine, and then I will go on to give a quick example about internet ads and purchasing behavior. So the Salk vaccine was developed to deal with polio. Polio is a disease characterized by progressive muscle and joint weakness and pain, sometimes leading to paralysis. The first major polio epidemic in the United States was in 1916. 27,000 people suffered paralysis and 6,000 died. By the 1950s, polio was responsible for 6% of all deaths among 5 to 9-year-olds. While the disease was fairly rare, the virus was fairly common. Now, in the 1950s, vaccines were not de rigueur. They were not, these days, people get vaccines all the time. Even beyond the coronavirus, where people had choice, any school kid going to school in the US gets a variety of vaccines, including against polio. But at the time, this was a fairly new technology. While the idea had been around for several hundred years, it was not accepted as general public health practice. And some observational studies were done, and they did not support the effectiveness of the Salk vaccine at preventing polio. But then randomized experiments were implemented and showed that it was indeed effective. So it was adopted, lives were saved, there were parades in honor of the vaccine. It was a big deal, and headlines like this. Okay, so you would think that after an important demonstration like this, we would have learned our lesson about thinking carefully about causality. In many ways, we did, because of this and other things that happened around the same period of time. Various federal agencies were initiated, including, for instance, the FDA, which now approves drugs through and medical devices through a process of randomized experiments. And then other institutions have modeled that to try to establish standards for adopting policies and practices that are based on rigorous causal inference, generally randomized experiments. Okay, but you flash forward 60 years and you are in the era of big data, and suddenly you get headlines like this. The end of theory, the data deluge makes the scientific method obsolete. And in particular, this article said there is now a better way. Petabytes allow us to say correlation is enough. We can stop looking for models. We can analyze data without hypotheses about what it might show. Okay, so the big data led to big hubris. And here's a cautionary tale in that vein. In 2011, the US spent $31.7 billion on internet advertising. And the common wisdom was based on naive data science. They sometimes use fancy models, machine learning models, to do these analyses. But the basic idea of understanding causality was naive. Generally, clicking on ads was shown to be highly predictive of a good outcome. For instance, buying a product, finding a website. Therefore, it was concluded that internet advertising was highly effective, until people started doing quasi-experiments, randomized experiments to investigate this. Because the question is, what if shoppers would have bought the product anyway, right? Is the ad, clicking on the ad leading to buying the product, or are they clicking on the ad because they're already interested in the product? Well, results of quasi-experiments at eBay showed that for a particular set of products and ads, 99.5% of click traffic was simply redirected through natural unpaid search traffic. That is, almost everyone found the site anyway. Okay, so a lot of those ads are doing absolutely nothing. Of course, it depends on context, depends on the ad, depends on the product, how well known the company is, et cetera, et cetera. But a lot of it is probably wasted money. And yet in 2020, 152 billion was spent on internet advertising in the US. We ignore causal inference at our peril. Okay, so why don't we just do it right all the time? Well, that's because causal inference is hard. Causal inference at its base level is about making fair comparisons. We want to be in a situation where the only difference between the two groups we're comparing is that one got the treatment and one didn't. But oftentimes our data don't look like that. We have a group who got the treatment, a group who didn't, and they're quite different based on their observed characteristics. Even more insidiously, they might look exactly the same on their observed characteristics, but in terms of things we can observe, they might be very different. Okay. So to make this idea of fair comparisons more concrete, we will talk about some causal inference building blocks. And in particular, we need to understand the idea of counterfactuals. Why do we need counterfactuals? Well, consider the following scenario. Joe is struggling in math. Joe uses an online tool for extra help with the material. Joe scores poorly on the subsequent math test. Did the online tool cause the low test score? The question is, what would have happened if Joe had not used the tool? We can't even conceptualize the idea of the tool causing the test score without knowing what would have happened in that counterfactual scenario. So causal inference requires a comparison of counterfactual states. In this case, Joe after classroom instruction alone and Joe after classroom instruction plus using the tool. The effect is defined as a comparison between those two potential outcomes. So this formalization of the counterfactuals are called potential outcomes. The problem is we can't see both potential outcomes at the same time. So we have a missing data problem. Either we're missing our Y0 or we're missing our Y1. So like in most of statistics, to make progress, we have to make some assumptions. The really tough ones in causal inference, the ones that we have the hardest time believing, are the structural assumptions. So of course, those are the ones we make and often just ignore. So the key one in most of causal inference is called ignorability. In other fields, it's called no hidden bias, selection on observables, all confounders measured, exchangeability, exogeneity. And technically, this is formalized as the potential outcomes being independent of the treatment assignment, conditional on X. How do we think about that? Well, one way to think about it is by first thinking about randomized experiments. In a completely randomized experiment, that independence holds unconditionally. The two groups are the same on everything that we care about. In a randomized block experiment, the randomization happens within subgroups or blocks. Then that ignorability holds conditional on the blocks, okay? And what we're hoping we have in observational studies is that we have something that's like a very complex randomized block experiment. So if you look within a block defined by people who are the same on all their covariates, we have something that looks like as if randomized, where we're hoping in that case that our potential outcomes in that subgroup are independent of the treatment assignment. We're hoping that within that group, it's kind of like a flip of a coin whether or not they got the treatment. But that's contingent on measuring the right set of covariates. So again, we can use randomized experiments in causal inference, but it's hard to do because of logistical, ethical constraints. It may be limited to narrow questions or populations, still challenging to understand when, why, and for whom, and it still can be challenging to understand effect heterogeneity. Within observational studies, we can make progress if we make these assumptions, but we have to typically adjust for many covariates to justify our ignorability assumption. And the more covariates we use, the stronger our parametric assumptions. So most of the work in causal inference gets at this idea of how do we appropriately condition on X. And that's where our parametric assumptions come in. Our parametric assumptions are in some sense easier to test, but if you want to understand whether, for instance, in a linear regression, you've satisfied all your parametric assumptions when you've got 1,000 covariates or 100 covariates or even 20 covariates, it's pretty challenging. So let's suppose in our example with Joe that we also have data on everyone else in the class. Okay, so Joe indeed did not score well on this post-test relative to everyone else in the class. But that's not what's important for causal inference. What's important is what would have happened to Joe, something down here, if Joe had not used the online tool. Okay. So now let's also suppose that we have only one confounder, a previous test score. So this is going to help us understand how we can use modeling to get at our missing potential outcomes. Because really, if we have all this data, it becomes, and if we assume ignorability, this becomes just a modeling exercise, right? I know what Joe looks like after receiving the treatment. I just need to predict what Joe would look like without the treatment, right? So I need to know Joe's treatment effect. And ideally, I want to know the treatment effect for everyone in the class. But notice in this example, as in many real life examples, there's a lot of heterogeneity. Depending on what your initial test score is, your treatment effect, that is the difference between what you would look like if you don't get the treatment and what you would look like if you do get the treatment, those differences vary a lot depending on what your initial pretest score was. Okay. If we could get all of these 8 individual level treatment effects, we could average them up to get any kind of average treatment effect we might be interested in. For instance, the effect of the treatment on the treated would just look at all of these treated observations, all the ones in red, and look at all of their causal effects, take the average of all of those. And the same thing would happen for the effect of the treatment on the controls. The AT would look at the average of all the individual level treatment effects across everyone in our sample. Oops, didn't need that one. Okay, notice that what's been hiding in the background here is this dashed line. The dashed line shows a linear regression fit to the data. So linear regression is not doing a good job for a number of reasons. It's, in this case, estimating an effect as if it's the same for everyone. Obviously, we could throw in interactions. In this particular example, that actually wouldn't help a lot. But the real problem here is that we have lack of overlap, right? So all down here, I don't have any treated observations. And up here, I only have one control observation. So that makes it really hard to even get the best approximation to this curve with a linear fit, because I don't have enough data to get an approximation to this curve for the entire covariate space. Okay, so wrong model, lack of overlap combines to some messiness. All right, so what's the role of machine learning? So machine learning can allow for flexible fits to these kinds of surfaces, right? So if you think this is hard with one confounder, imagine what it's like with 20, 40, 100, 500. Machine learning allows us to do that without having to think hard about it. It will find the best fit. This example with our data has shown, I'm showing just a simple regression tree fit to these data. Okay, so with only 6 terminal nodes, so it just creates a nice little step function. Obviously, the step function is doing not a perfect job. It's a pretty crude fit to these data, but the idea is that there are a lot of machine learnings based on things like building blocks like regression trees that can do a better job. And Bayesian additive regression trees is one such algorithm. The BART fit to these data shows up in the red dashed line here. So it's capturing that curve quite nicely. It starts to deviate a little when it doesn't have data, of course, and we'll come back to that. All right, so how does BART work? So BART starts with a single regression tree, which hopefully audience may be familiar with a regression tree fit. It's just dividing into mutually exclusive subgroups of the data and taking the mean of each subgroup as the fit to our data. And then what BART does to get a better fit is that it uses a sum of trees. This is not a tree averaging. It's not like random forest. It is a sum of trees. So the way you can think about this is first fitting a very simple tree to the data, taking the residuals from that, and then fitting another small tree to those residuals. Because what are those residuals except for everything we haven't yet explained? So a simple boosted regression tree would look like this. And BART takes that boosted regression tree and dumps it into a Bayesian inferential framework. And rather than the kind of frequentist ways of avoiding overfitting, which are a little clunky and cumbersome, it avoids overfitting using a really clever prior, and then it's fit using MCMC. Okay, and again, it does a great job of fitting nonlinear surfaces. So how do I use this for causal inference? Well, remember, all we're doing in some sense, once we assume ignorability, is making predictions of those missing potential outcomes. So I can fit my model to a data set with some covariates, where I've got the treatment assignment here, and I've got an outcome, which in this case is a child test score. But when I make predictions, I make two sets of predictions. I can predict what my outcome would look like if everyone in my data set did not receive the treatment. And I can make a prediction of what that would look like if everyone in my data set did receive the treatment. Okay. Now the Bayesian piece comes in because not just, I could get an individual level estimate of a treatment effect by just taking a difference between these two predictions. But the nice thing about being in a Bayesian framework is I actually understand the uncertainty about each of those predictions. So for this person, the first row in my data set, I can get a posterior predictive distribution for their Y0, a posterior predictive distribution for their Y1, and then the difference between those two is the posterior distribution of the individual treatment effect estimate, for instance, for Joe in my data set, okay? This is nice because for everyone, I can get estimates. Here is this shown in my original data set. I've got for each treated observation there, I'm showing you my uncertainty interval, both for their Y1 and their Y0. Since I'm focusing on the treated, I know a lot more about their Y1 because I see their Y1. It's their Y0s that I have more uncertainty about because I'm imputing, in some sense, their Y0s based on information I have from other people in the data set who look like them but didn't receive the treatment. Notice that when I don't have data, my uncertainty gets big. That's great. That's exactly what we want to happen. And that's something that happens because I'm using this Bayesian framework, which is conditioning on the information that I actually have. Okay, notice I get more information again when I see this data point and the interval goes down. I'll show you an example later when I don't have that data point. Then again, I can combine these to get individual level treatment effects. So this shows instead on the y-axis the actual treatment effect. So the actual treatment effect is in red, and the intervals for the treatment effects for each of my individual level treatment effects for each person in my data set are shown here. And notice when I start to run out of overlap, I run into problems. Compare this to the regression estimate, including uncertainty intervals. The regression estimate here is constant, and it's very confident in itself, even when it really shouldn't be. Okay, so BART, what's the evidence that this can do well? Well, BART has been either the top or one of the top ranked methods in all of the causal inference data analysis challenges that have been held in conjunction with the Atlantic Causal Inference Conference. For a few years, it wasn't held because of COVID, but all the ones that have existed, it's really dominated. And it regularly outperforms propensity score methods and also other machine learning methods. There have been a bunch of scholarly articles as well. This is a smattering at this point. There are many, many more. And so what are some other nice features of BART? I'll talk briefly about a few of these. It helps to detect and remedy violations of common support. It can explore sensitivity to violations of ignorability. It identifies treatment effect heterogeneity. It performs well when generalizing to other populations. It produces coherent confidence intervals. And recently it's been extended to accommodate multi-level models through a semi-parametric version called Stand for BART. So for common support, as I referenced later, here's the same data, but where I've excluded that data point up here that was helping to anchor some of those counterfactual predictions. And you can see that once that data point is not there, I really start to do poorly. So how do I know how far can I extrapolate beyond the range where I actually have data on the controls? Well, one way is to compare the uncertainty that you see here versus the uncertainty that you see here. So I've proposed two different strategies based on that. That was in a paper published in 2013, didn't include the reference here. Anyway, with Yu-Sung Soo, the reference is at the end. So that's kind of a neat feature of BART. I've also incorporated the Bayesian framework, makes it easier to kind of add in components to the model and take them out. So we've got a semi-parametric version of BART that allows us to include a latent variable for an omitted variable that would be an omitted confounder. So then we can perform the thought exercise of what would that treatment effect look like if I included that confounder. So here's a contour plot showing various contours of treatment effects that would arise based on different assumptions about how that confounder, how much confounding there is. And that's captured in a package called TreatSense. The treatment effect heterogeneity you saw in the earlier plots, right? So we can get a posterior distribution from BART, but we know that we can actually get different posterior distributions for each person in that data set, right? Which allows us to explore heterogeneity. A nice thing that you can do then is to throw those individual level treatment effects into a regression tree with covariates as the predictors of that regression tree. This helps us to explore our treatment effect heterogeneity and allows us to pick out which confounders are driving that heterogeneity the strongest. Okay, so that once you find those subgroups, you could then plot posterior distributions for each of those subgroups to get a sense of whether those differences in treatment effects are meaningful. As another example, there was a different data challenge associated with the 2017 Atlantic Causal Inference Conference, where the people who arranged for this challenge simulated data to mimic real data from a very large scale national mindsets experiment. And they built in a bunch of treatment effect heterogeneity and had the participants, there were 11 or 12 of us, try to find what covariates were moderating the treatment effect. And one thing that we found, at one point I did a plot of individual level treatment effects. Actually, these were school level treatment effects versus two of the confounders that they had asked us, sorry, they weren't confounders, it was a randomized experiment. Two of the covariates that they had asked us to see, determine whether they are moderators. When we didn't explore the data by individual level treatment effects, we saw these curves and thought, oh, I guess there's something really going on here. When we looked individually, I saw this pattern and thought, oh, wow, there's some weird groups here. So I ran it through a regression tree, realized that actually there was a predictor, there was a very strong predictor of this heterogeneity that we're seeing in the plot, and it was urbanicity. And when we plotted by urbanicity, we could break these down by groups. So if you don't condition on urbanicity, it looks like fixed mindset and achievement are moderators. Once you do, that effect really drops away. Okay, so how would you use these tools if you wanted to? Most of the things I've talked about today are in a package created by my collaborator, Vince Story, called BART Cause. The BART mechanism, there are also a bunch of BART packages. His is the best, I'll say. He created dBARTs, which he's continuously updating and has some great features. So that sits on CRAN. If you're an R user, it's pretty easy to use. We're also pretty responsive or particularly Vince's, when people respond with comments or We try to also create extensions when people ask for them. Since then, we've also created a package called Stand for BART. So that was driven by the idea that most of the current machine learning methods aren't optimized for semi-parametric model. So maybe that some piece of the parametric structure, then we should build that into the model, or you should be allowed to build that into the model. Also, most machine learning methods assume that data are IID, even though many tout themselves as if they don't. They do. So if you want a more complicated variance structure, that's not always easy to do with machine learning methods. So we wanted to incorporate those features. We partnered with the STAN folks. STAN is a general Bayesian inference algorithm, uses efficient Hamilton MCMC. Their claim is that it works well or gives dire warnings with few false positives. Lots of references on this. And so STAN was helpful because it's an efficient algorithm to sample from posteriors that aren't necessarily Gaussian. And partial pooling is important for individual and subgroup treatment effects. Okay, so our new combined model basically has a piece that's parametric and a piece that's non-parametric. Okay, not a lot of time to go into the details on that, but hopefully it gives you the flavor. It can also fit binary response through latent variable formulation. Okay, how does Stand for BART perform? We just published a paper in December 2022, a small smattering of the many results from that paper. If you compare Stand for BART versus some of the other BART flavors, it does a little bit better. It's hard to tell from this plot because we also compared it to parametric models for dealing with multi-level structures. And when we have nonlinear response surfaces, it's just doing so much better. And Stand for BART compared to the other BARTs that don't accommodate this kind of structure, it does better at getting shorter and more appropriate confidence intervals. So this is for estimating an average treatment effect. We also see gains in performance when estimating individual level treatment effects and kind of everything in between. So here is a plot that shows performance with regard to individual level causal effects. And again, we're seeing the best performance from the Stand for BART models, slightly better than the vanilla BART and way better than the parametric models. Okay, now my baby right now, my project that I'm most excited about is called Think Causal. Think Causal is, so those two are both available in R on CRAN. If you're an R user, that's great. Not everyone uses R, right? And so I think as statisticians, we tend to do a really bad job of writing about our work in ways that other people can access, talking about our work in ways that people can access, and providing software for our research methods that other people can access. So that's what motivated Think Causal. Think Causal is a standalone. Right now, it's based on the internet. It's almost entirely built using R Shiny. Actually, it's a fantastic advertisement for what you can do with R Shiny. We've got a little bit of Java and HTML thrown in there, but mostly R Shiny. Basically, it's scaffolded, user-friendly access to sophisticated causal inference tools. So at its core, it is BART Cause, but we have this overlay of this very user-friendly software where people can point and click to upload their data, to choose their estimands, to explore their data using all kinds of ggplot-based visualizations. Then they can download those visualizations. They can point and click to fit the BART model, et cetera, et cetera. And then at the end, we actually are working on providing a full reproducible code for everything that was done. We've got diagnostics. We even help people interpret the results at the end of the day. They can all these, what the features that I talked about with heterogeneity, they can do. So they can get posterior distributions for average treatment effects, but can also pull them out for any subgroup they want, and we can provide plots even for individual level treatment effects. So it's ongoing work. We're really excited about it. Perhaps the best part about this software is that it has educational components for just-in-time learning. So if you get to a point in the software where you say, oh, I'm being asked to choose an estimand, I don't know if I want to estimate something for an average treatment effect or the effect of the treatment on the treated, it will bounce you out to a full educational component on causal estimands, where it's like a kind of New York Times looking, scrolly tell, where you scroll through and you get various visualizations. They're interactive to tell you a story to help you understand potential outcomes, causal estimands, so that, and there's even a little quiz at the end to test your learning, so that when you go back and have to make that decision, you're making an informed decision, as opposed to what most people do with software, which is just choose the option that they think sounds good, someone else has used before, whatever. The person who did something similar in their lab used before, even if it's not appropriate for their data. We really want to have, to make this easier on the user, but also to have them understand what they're doing. Okay. So I talked more quickly than I thought I would, but so here I am at my conclusion. BART provides a flexible strategy for accurately fitting nonlinear response services. This can improve estimates both of average causal effects as well as heterogeneous group and individual level causal effects. The Bayesian likelihood framework is really crucial here because it allows for accurate uncertainty quantification without sacrificing sample size. So in other methods, they bootstrap, which can create all kinds of problems. They're not always, the uncertainty intervals that come out of bootstrapping, first of all, it's very computationally expensive, but they're not always appropriate for what needs to happen. Also, in order to get kind of honest inference, a lot of the machine learning methods need to have a holdout set. We don't need to have a holdout set. So that's lovely. It also allows us to have flexible inference for a wide variety of estimates. So starting with those individual levels and then building up to whatever average treatment effect is a really, really nice feature. And then the tools that exist so far, or at least the ones that I've been a part of creating, are BART cause, again, which the bulk of what I talked about today is sitting in BART cause, which sits in R. Stand for BART, which also sits in R on CRAN. And then the new software, if you've got collaborators who, you don't have time to help, but they need to do something with causal inference and they don't want to sit and fit 30 propensity score models or whatever it is that they would have done otherwise, consider pointing them towards Think Causal, which is this standalone software that basically anyone should be able to use. Okay, thank you. And here are some references.
Thank you so much, Jennifer. This was really fascinating. I think a very clear talk. Don't have any questions from the audience at the moment, but I do have a couple of my own. Great. So my first is, why BART versus something else like a Gaussian process model or another non-parametric Bayes method?
Yeah, you could use any of the above. It's just, I got started with BART years ago because I just happened to be giving a poster in like 2000 or something next to one of the BART developers. And I was actually advocating for propensity scores, and he's like, why don't you just use BART? And I was like, what are you talking about? I had no idea what he was talking about. So, that kind of started me down this road. And it just has proved to be, it's possible that there just hasn't been enough work. We started going down that road for a while and weren't getting great results from Gaussian processes, because at one point we wanted to make a hybrid BART and Gaussian process, and I think actually people have attempted to do that. So it's not necessarily that couldn't be the right way to go. It's just it hasn't been explored a ton.
Um, uh, One thing you mentioned towards the beginning is this issue of model checking, and I'm curious what, if any, model checks you tend to use with these, like posterior predictive checks, leave one out, cross-validation, any of these other methods, how those play into your workflow.
Yeah, it's a great question. So lots of things. So first of all, for the MCMC algorithm, for the standard BART implementation, the advice was always just to look, the only identifiable parameter in the model is the error term, right? Everything else is exchangeable and just can flip around at a moment's notice, everything that's particular to the trees. So they would look at the error term. That's fine to look at, but it's not sufficient. So what we tend to look at in our work is also any treatment effect estimate that you care about, save an estimate of that from an iteration and track those over time. We also, it used to be the advice was to, you can probably just do a single chain. And then it was, well, maybe we should do 3. Some great work by Nicole Carnegie has shown that really you should probably be doing 10. So we now always do 10. So on the Bayesian side, there are those pieces. Also, it assumes things like normal error terms, right? That may be reasonable, it may not. So Vince and I and my research director, George Parrott, were involved in a data analysis competition last spring where the error terms were highly skewed. And we only saw that because we did residual plots, right? People don't do residual plots anymore, right? So we did a lot of residual plots and oh dear, it was scary, right? And you're not going to get good predictions if you can't capture that error term. We've got posterior predictive distributions. We are assuming we know that error term well. So we now regularly do residual plots, although I'm realizing we haven't put that in Think Causal, which we should. Making a note. I think those are the big ones. And overlap. So we check, that's built into Think Causal too, there and into BART cause overlap plots. If you should be dropping them, if there are observations that you shouldn't be making inferences about because you have way too much uncertainty, then you should probably drop them and let your reader know that you've done that.
Thanks. I think Giannis has a question. I'll let him ask it himself.
Yeah, actually, maybe that's the first question, and then I have a follow-up. Can you compare BART, or can you comment BART compared to XGBoost and sort of gradient boosting machines, which are also a sum of trees, right? So
yeah, I mean, it's just performing the inference in a different way, right? So basically, the mechanics in terms of the mean structure are basically the same. The one main difference, which borders on being part of the inferential part, is that in those, your 50th tree is very different from your first tree. It means something very different. And in BART, because we're iterating through those trees again and again and again through the Gibbs sampler, those trees are all exchangeable. So that's a difference that I know the BART people like to tout. And then it's just the uncertainty quantification. Well, so and then there you always have to do something to avoid overfit, right? So in those kinds of sum of trees models, usually you just multiply the fit from each tree by some small constant. You choose that small constant through cross-validation, typically, which is cumbersome, but works. In BART, that shrinkage parameter basically is defined by the prior. They've got a very clever way. Their default prior does a great job. So there was some early BART work that I didn't include slides on where they compared their results to just kind of standard boosted regression tree models. And their default prior performed basically equivalently in terms of RMSE to those where they're choosing their parameters through cross-validation. If in BART you choose your parameter through cross-validation, you do better. Typically, I mean, or at least in those settings, they used at that time, I think like that kind of, there was some UC Irvine, I don't know, set of data sets that were popular in the early 2000s, and they performed all kinds of,
And another question, in many applications, one would like a model that is interpretable. How interpretable do you think is a model that may involve a sum of many decision trees?
No, yeah, it's a great question. So I have lots of thoughts on that. When there are people working on interpretable versions of BART where they're trying to project it down onto a smaller space. So I'm thinking of like Richard Hahn, Carlos Carvalho, and Jared Murray. I saw them give a talk on something like this before. So I know people are working on this and care about it. The problem is if you're saying like which of an infinite set of 3-parameter models does this best, you could look at it is infinite, right? But people have made some progress. I often feel like in causal inference, people overinterpret their models. Like it's really hard just to get that one estimate that's correct, right? And so in social science, there's this long tradition of let's fit a model where we've got like 20 predictors and let's interpret them all, even though they're all conditional and everything else, right? And there wasn't a lot of thought. So the conservatism of this, where it takes a lot of effort, so you can get subgroup effects. That's a more interpretable model, right? If I'm now looking at treatment effects and how they vary across subgroups, it takes a little bit more work to do that. I kind of like that it takes a little bit more work to do that because I don't want people necessarily interpreting parameters from other parts of the model where there are non-causal interpretations, because they're almost definitely gonna do something wrong. So I've got a whole other research stream on how people misinterpret evidence from research findings, and it's terrifying.
All right, thank you.
All right, maybe I'll ask just one more question before we wrap up, which is, so you talked at the beginning about how inevitably you have to make all these structural assumptions, and you sort of briefly mentioned sensitivity analysis. So I was wondering if you could just talk a little bit about that, and maybe in particular how BART helps or figures into that.
Yeah, so there's typically there's 2 flavors of sensitivity analysis. There's sensitivity analysis that's almost entirely non-parametric. So Paul Rosenbaum has done beautiful work with really non-parametric views of frameworks for sensitivity analysis that play with this idea of what if there's this big confounder that we didn't get to observe? How would that influence my results? So this was all inspired by classic work, actually by Kornfeld in the 50s, where people were debating whether or not the relationship between smoking and cancer, for instance, was causal. And Kornfeld, who was kind of like not a well-known guy at the time, but made this really clever argument of, well, what would it have to look like? If you're saying this relationship isn't causal, that means there's some confounder that's really driving, right? Both smoking rates and the rates of cancer, right? What would that confounder have to look like? And he showed that it would have to it would have to nearly perfectly predict smoking, I think, and be something like 10 times more prevalent in people with cancer than not. I'm getting the numbers roughly wrong, but they're ballparky, right? And so people have played off on that idea, including Rosenbaum. Rosenbaum has great work doing non-parametric stuff with that. The problem is it's really hard to then make those sensitivity parameters interpretable, right? I had done some work, and others had, actually inspired by work by Hito Imbens, with parametric models where we say, well, like imagine if we had this unobserved confounder in a regression model with the treatment, what would the coefficient look like? Statisticians know how to think about coefficients in models. We're pretty good at that, right? And what would it have to look like in the outcome model? Okay, so that's good and interpretable, but uses the non-parametric. Uses a parametric model. Yuck. Don't want to use the parametric model. So this work with BART is combines those 2. So we keep that framework where you can interpret the coefficient on the unobserved confounder nicely as a coefficient in a regression model, but everything else that you're conditioning on, you condition on non-parametrically through BART.
I see. Okay, so you maintain the parametric component for that sort of confounder that you don't know, but everything else you're saying is still non-parametric. Is that right?
Yep.
Okay, got it. Well, great. Thank you so much, Jennifer. I think since there don't appear to be any more questions, we'll wrap up here. And hope everyone will join us for the next one in the series.
Thanks so much for having me.